Guys, this is Anand from VIT Chennai, and today we'll see a full PPT on curve fitting reverse curves. So first we'll start with compound curves to understand the basics of reverse curve fitting. A compound curve basically consists of two, maybe more circular curves between two main tangents joined at a point of compound curve, which is we can call PCC. Curve at a PC, which is point compound curve, is designated as 1, R1, L1, T1, etc. And maybe a curve at PT is designated as 2, R2, L2, T2. So we have point 1 and point 2, both designated as PC and PT. You can see in the figure that there is a common tangent between PC and PT, and the PCC is the point compound curve. Now we have the elements of compound curve. PC is point of curvature, PT being the point of tangency, PI being the point of intersection, PCC being point of compound curve, which as we saw in the previous slide. T1 is the length of tangent of the first curve. T2 length of tangent of the second curve. Again, we saw this in the first slide. A1 is the vertex of the first curve. V2 vertex of the second curve. I1 and I2 is central angle of the first and second curve respectively. I is the angle of intersection, which is equal to I1 plus I2. That is the central angle of the first and second curve summed up. LC1 equals length of first curve, LC2 length of second curve, L1 equals length of first chord, L2 length of second chord, L equals length of long chord from PC to PT, that's point of curvature to point of tangent. T1 plus T2 is the length of common tangent measured from V1 to V2. As saw V1 and V2 are the vertex of the first curve and the vertex of the second curve. Theta equals 180 degrees minus I. X and Y can be found from the triangle V1 minus V2 minus PI. L can be formed from the triangle PC minus PCC minus PT. That is the point of curvature minus point of compound curvature minus point of tangent. Next, we see finding the stationing of PT, that is point of tangential. Given the stationing of PC, we have point of curvature. The stationary point of tangent equals stationary point of curvature, LC1. As you saw, LC1 is the length of the first curve plus LC2 stationary PT, which is the length of second curve multiplied with the stationary point of tangent, which is also equal to the stationary point of curvature plus LC1 plus LC2, which is the length of first chord and second chord as you saw from previous slide. Next, if the stationing of PI is given, which is point of intersection, we have the formula would be stationary PT, which is point of tangential. It'll be equal to point of stationary point of intersection minus X minus T1. As you saw, T1 is the length of tangent of the first curve plus LC1 plus LC2, which is length of second chord and length of the first chord. Now we finally dive into the reverse curve. Reverse curve, though pleasing to the eye, would bring discomfort to motorists or cars. It depends on what you prefer. Running at design speed. The instant change in direction at the PRC brought some safety problems. Despite this fact, reverse curves are being used with great successes on park roads, formal paths, waterway channels, and the like. Here we have a diagram on reverse curves. As you see, it's an S, and basically reverse curve is when you travel on one side and after a particular point, which is the PRC, you go in the straight opposite direction. These are hard to make, and as we said, it brings discomfort to motorists running at design speed or at the uniform velocity. Here we have PC, PRC, and PT. As you know, point PC is point of curvature and PT is point of tangent, and they both have a common tangent due to the coinciding curves. Next, we have elements of reverse curves, the same as we saw in compound curves. PC equals point of curvature, PT being the point of tangency, PRC being the point of reverse curvature. T1 is the length of tangent of the first curve, PT and second curve, same basically as compound curves. V1 is the vertex of the first curve, V2 being the vertex of the second curve. I1 is central angle of the first curve, I2 is central angle of the second curve. LC1 is length of the first curve, L2 length of the second curve. L1 length of the first chord, L2 length of the second chord. T1 plus T2 is length of common tangent measured from V1 to V2 being vertex 1 and vertex 2 of the first curve. Now to find stationing of PT, we are most probably given the stationing. If the stationing of point of curvature is given, the formula would be the stationary PT or standard point of tangential is equal to the standard point of curvature plus length of compound curve plus the length of second curve in times the stationary point of tangency, which is equal to the stationary point of curvature plus LC1, which is the length of first curve plus LC length of second curve. Now, if the stationing of V1 vertex 1 is given of the first curve, stationary point of tangency would be equal to the stationary V1 vertex 1 of the first curve minus T1, which is length of tangent of the first curve plus LC1, which is length of the first curve plus LC2, length of the second curve. Next, we have reverse curve for non-parallel tangents. So now, non-parallel tangents and parallel tangents. It's not just simple reverse curves for straight lines or S lines. The following figure is an example of reverse curves of unequal radii connecting non-parallel tangents. So now we see two curves of completely unequal radii. One is bigger and one is smaller. The first one being bigger and the second one being smaller, connecting non-parallel tangents. These tangents are not parallel. They have an angle of I2, as you can see, and there's a back tangent and the forward tangent. Now we have reverse curve for parallel tangents shown in the figure, and this figure is an example of reverse curves of unequal radii connecting two parallel roads. Now two parallel roads are connected, but here the forward tangent, backward tangent, unlike the previous slide, is parallel to each other, and the angle between them is zero, nil. Now we have a figure of common tangent, and I will explain this in the next slide. There is a common tangent S. This is the basic redefinition of reverse curve fitting. The alignment from PC point on curve to PRC point on reverse curve to PT or point on tangent above is known as reverse curve. So here we see the PC, the PRC, and PT connecting in a very S-like manner, a very basic reverse curve fitting. The driver usually has to go through a curve in the one direction and immediately adjust to steer in the other direction. So there's no time for the driver to adjust to coming out of the curve. As you can see in this figure, the driver comes in straight from the PC, passes through the LC1 through the T1, and reaches PRC, and then immediately turns the completely opposite direction as it travels the common tangent LC2 and finally reaches PT, point of tangency. So now we typically design rows such that there is a tangent or a straight line in between the curves. This allows the driver to make adjustments before going to the next curve. So as we see here, there is always a tangent or straight line between these two curves. So now here along LC1 and LC2, and as he passes through PRC, the driver makes changes to his speed so as to adjust and completely go through the PC and PT. Now there is a generalized equation of reverse curve and derivation of its radius. It's basically used in railway and highway engineering. Now in most countries, the measurement of curvature of curved track is expressed in radius. So basically, the shorter the radius, the sharper the curve is. It's very common. It's common sense. For sharper curves, the speed limits are lower to prevent an outward horizontal central force, which basically overturn the trains by directing its weight forward towards the outside rail. The cant may be used to allow high speeds over the same curve. Now we see that the relationship between speed and tilt of a train or a car, it depends on which we prefer. If the reverse curve is used in railway or highway, can be calculated mathematically. We start with a formula for a balancing centripetal force. Inside force, theta is the angle by which the train is tilted due to the cant, r is the curve radius in meters, v is the speed in meters per second, and g is the standard gravity, approximately equal to 9.8065, which is 9.81 meter per second square. Now the formula is not very clear, but I'll tell this to you. Tan theta equals v squared by gr, v squared being the velocity in meters per second, square by g is the standard gravity multiplied by r, which is curve radius in meters. Now you rearrange this cross r, multiplied by r goes the other side, you get v squared by g tan theta. Geometrically, tan theta can be expressed approximately for small angles, maybe in terms of the drag gauge g. The cant HA and cant efficiency HP are all in millimeters. Now replacing tan theta with what has just been proposed in the previous point, we get tan theta is almost equal to sine theta, which is almost equal to HA plus HP by G. Thank you guys, that's all for this PPT.